Okay. Good afternoon, everyone. Welcome to the Wednesday afternoon session of the CHPC NITheP Summer School, and Zurab will continue his story about the mathematical logic or logic of the proofs in Python. Zurab, it's your show.
Thank you very much, Ilya. So just wanted to warn everyone that I have COVID. And it's nice that the COVID does not get transmitted through a Zoom meeting. And also it's nice that it wasn't very bad and I seem to be recovering quickly. But I do apologize for not keeping to my promise what I said I would have done over the weekend, which I didn't do because of that reason. That's from the last lecture. I did, however, take a look at some of the submissions and remarked some of them as well. And it was nice to see some students, some participants doing well there. Not everybody is doing equally well, but we can always bring into this session a discussion of any misconceptions that you might have. So feel free to ask questions during the session. I have also updated a little bit the lecture notes. I've added another section, which I think might be interesting for us to have a look at. And also there was the last section, which we never properly looked at together. So let's do that now. Let's begin with that. It's the section that was called Axioms. And we're going to take a slow approach with that. Great. So let me share my screen. Okay. Ilya, could you please confirm that you can see my screen?
Yes, I could see your full desktop screen, and now I could see the paintbrush, I assume.
Okay, great. Thank you. We are somewhere here in the lecture notes. In section 8. Maybe I should also take the opportunity to mention that at the previous lecture, we said something about the ontology not being quite correct at one of the pictures of this section. I fixed that, and I also added some explanations. I think I put a message on Slack explaining exactly what I fixed as well. So if you want to go back and have a look at that in terms of ontology of statements, it has now been fixed. Okay. So what are axioms and how they relate to theorems and proofs? Well, to prove something in mathematics, to prove something, I mean, not just in mathematics, I mean, in any area of science, to prove something means to derive that thing from other facts. And these facts might be experimental data and so on. But of course, if you're only relying on experimental data, what if the experiment wasn't right? Yeah. So you want to have more refined technology for confirming that that your starting point from which you're deriving things is correct. Unfortunately, though, it's not possible. The best you can do is to make sure that your starting point is a precise mathematical statement. Why can't you, any intuitive explanation, why can't you make sure that your starting point is correct? Okay, so imagine you're confirming that your starting point is correct. So you'll have to confirm it based on some knowledge, right? You cannot just confirm something if you're empty-headed, right? Whatever you will use to confirm that with, then the question is whether that is correct. and so the one can go on infinitely. So we have to start somewhere. Even in science, we have to start with a set of beliefs. These are very minimal beliefs, things that have been not proven, but at least justified by numerous experiences and experiments and so on, but they're still beliefs. So we can't be 100% certain that those beliefs are correct. So these basic beliefs from which we try to build the rest of science are called axioms. There is not really a necessity, if one thinks about it, there is not really a necessity to have axioms stated separately. Every time you want to prove a theorem, you can just say, if I believe in these things, then I can make these and these conclusions, right? But repeating your basic beliefs every time with every single theorem is going to waste a lot of your time. So you want to have those things that you are going to use a lot stated separately. And then that's how the need for formulating axioms arises. So we have here an example of an activity. We have an activity which will demonstrate an example of an axiom. There are two in this first activity we're looking at here. And so I apologize to those of you who already have looked at this section. The thing is that the assignment, which was based on the notion of axiom, only, I think, 3 participants submitted the homework, and their submissions were correct. But because nobody else submitted, then I thought that it probably means that section 8 still needs to be covered in this session. So you will have to be a bit patient for a little bit, those of you who already have gone through this part. So at the start of section 8, this activity that we have here, it gives us an illustration of how to create axioms in Sophia. So I'm going to now open my Spider and also mute my phone. Sorry about that. Okay, so let me copy paste this code. Oh, something happened there. I'm going to copy paste this code and run it. And let's now see what we get. So we have 2 axioms here. As you see on the output, we have axiom stating that everyone has a friend. And we have another axiom stating that Sophia exists. So these are basic beliefs we would want to use in future theorems to be proved. And the way as I said, it's impossible to prove axioms. So the way we justify this is to make sure that these are reasonable beliefs, right? Certainly the belief that everyone has a friend, that maybe one can argue whether it's a reasonable belief or not. Maybe it's not even true. But if perhaps we consider only those people who do have friends and just look, when we say everyone, just mean only these people, then in that context, this might become a reasonable axiom. And then, of course, the second axiom could also be argued whether it's reasonable or not. What does it mean to exist? If it just means that the file sophia.py is on my computer, then perhaps we can also accept that axiom. Okay. The first activity asks us to explain what these axioms state, but before we do that, let me link the output with the input. We import Sophia as we usually do. It's a common step. And then you see here, we're introducing an object called A1, and we're equating that to sophia.prop. So this is a proposition object from the Sophia module, and we are giving a name to it. So at this point, A1 is neither an axiom nor a theorem. A1 is something that could evolve into an axiom, or it could evolve into a theorem, depending on what we're going to do with A1. You might recall that when we were building up theorems, we did the same first step. We introduced some object that was a Sophia proposition. The command that turns A1 into an axiom is this command .p. It is short for postulate. So the idea here is that with this command, we are telling Sophia what the axiom states, and we're also saying that A1 is now should be seen as an axiom. And so after this command, we will not be able to build a proof for it. So unlike in a theorem where we never tell Sophia what the theorem should say, we always try to give an argument for the proof, and then Sophia herself comes up with what the theorem should be. Here, it's the other way around. We tell Sophia what it should be because she's not gonna be able to generate it from any kind of proof. And if we look into the expression itself, what it says, so let's maybe look at it on this side. Well, intuitively, we're already given a hint. This is supposed to say that everyone has a friend. Let's see how this is achieved here. If I look at ontology of this statement, right, maybe it's useful to draw the ontology, especially that there are still some participants who are not quite correct in their submission on ontology. So we've got this statement. I'm just copying it down here. Is friends with X. And the first thing we notice that this is a statement, of course, right? And so being a statement, which inside it has a formula, it decomposes into that formula. So it's one step here only, where we just extract that formula out from the statement. So here we have a formula. Okay. Now, of course, we have a statement because remember, when we create a statement, what we mean by that is that we're claiming that something is true, and that corresponds to the idea that axiom is claiming that something should be true. We're believing that it will be true. We're not just considering the idea of everyone having a friend, we are believing that everyone does indeed have a friend. It's the difference between the two things. It's marked by stating it or living it in a formula shape. Now let's look at the further decomposition of the formula. So that formula decomposes into two statements, right? The left side of this column and the right side. And remember what the column represents. It represents implication. From left, we can derive the right side. So Y is friends with X. Okay, we're not going to need to go further into ontology. I'm going to stop here. So this would go further, but we don't need for now. And let's focus on this symbol here, the meaning of that symbol, right? So we're told that whenever the left-hand side is given to us, when the left-hand side is stated, right? The right-hand side can be derived from it. But what is left-hand side? It's a variable X. So it could be it could have any value, right? So we're basically told that whenever we are given X, it will be possible to give Y such that that Y will be friends with that X. So now think about it. We're saying no matter who you bring, let's temporarily call that person X when you bring that person. once you bring the person X, I will be able to find a Y. I will be able to bring Y, such that that Y will turn out to be the friend of X, right? So basically, I'm saying that every person has a friend. Yeah. Is that clear for everyone? Do you see with this explanation how this expresses exactly that everyone has a friend? Would be good to have some feedback on that. Oh, by the way, thank you for the good wishes. Great, thanks. So I got one confirmation that what we explained was clear. It's an important point which shows us the difference of variable appearing for the first time on the left side and on the right side. So the left side variable obtains the role for every. If you're familiar with some mathematics courses, you would often find mathematical statements stated like this: for every. Okay, there's even a symbol for that. For every X, we are saying we can find Y, and so this would be there exists. And the mathematical symbol for that is this. But now we don't have to worry about the symbols in Sophia, because we can detect whether something is for every or there exists, depending on whether the variable appears on the left of column for the first time or on the right. So Sophia is a bit simplified formalism than the usual mathematical one. And if you have seen these symbols before, you might also remember them from the definition of a limit, the epsilon delta definition. That's often very confusing. Sorry, I interrupted someone asking a question.
Sorry, Mpumalala have her hand up.
Please, yes.
Thank you. Prof, I actually want to ask that can we sort of like read out this statement using the language that you have stated, that for every X there exists Y, such that if we have Y, there will be corresponding X. Is that the correct way of reading it?
Yes.
Okay. And secondly, so basically converting that proposition, everyone is a friend, into like Sophia formalism.
What's the second question? I didn't understand that.
So basically, so what we have to write the proposition first and then convert it to Sophia's formalism.
Well, if depending which formalism is more natural for you. I've met some mathematicians who actually have been using Sophia without realizing that they're using something different from what exists. It's just that I'm one of those people who pushes that the Sophia thing is a good idea. It has never been documented anywhere properly yet as an alternative to the usual language, and I think that this alternative is easier to understand intuitively. That's why I'm trying to promote it. But if for you the quantifier language is already very familiar to you, then you might do that. You might first formulate things using quantifiers and then translate to Sophia.
Okay, thank you.
Does that answer your question?
Yes, it does.
Mm-hmm. So with Sophia, we don't say for every that exists anymore. We talk like this: given X, Y can be given so that Y is friends with X. So we're assuming that every time we have X, it's assumption, right? Every time we have X, then the conclusion must be that we also have Y. So it automatically creates this dependence that X could be arbitrary because the assumption doesn't have any restrictions on it, except that it's just X. And the ability for us to produce a Y is a conclusion. It says that there must exist at least one. So somehow the logic of implication kind of implements inside it these quantifiers from mathematics. And that was the illuminating point for me. I mean, when I realized that's basically what led to the creation of the Sophia language. Okay. Okay, let's go on. So that's what the first axiom says. And then we have the second axiom, and the second axiom just says, as you see, it just says Sophia, and it's written as a constant, not as a variable, because we don't want it to be something that can change value. We want it to have a constant value. We talked about constants before already last week, right? There is another way we could have written this out. We could have also written this out like this. Starting with no assumptions, so starting with empty statement, we can conclude that we have Sophia. So this would be another way of saying that Sophia exists. But it's a more complicated way. This is much simpler to just write it like this. And the rules of building proofs in Sophia that we have, they would enable you to switch between the two if you wanted to. Great. So these are the two axioms, and we've already explained what they state. So we've completed the first activity here. Now let's move to the next activity, which asks us to combine the program from the previous activity, in other words, this program, with the following one to see how an axiom can be applied in a proof. So all we do is just copy paste this part, put it here, then try to analyze what's happening here. Okay, so as a result, we get a theorem now, and the theorem starts for this, right? So we are introducing another Sophia proposition, S. As I already said before, at this point, S is neither a theorem nor axiom, but as soon as I start proving S, it now becomes a theorem. It can't be turned into an axiom anymore. So the first line of the proof, this command .c, recalls an axiom or maybe a theorem that has already been proved before. So if I look at the output, I can see this explanation right here in the output. This is my proof that I'm building through these just basically 3 lines. And if you look at the first line, if you look at the explanation where the first line was obtained from, it says, recalling everyone has a friend. So that means that we're recalling something we believe to be true already. And there is a name for that thing. The name is everyone has a friend. And we search for an axiom that under that name, we already know that the axiom under that name is exactly A1, right? Great. And then this is identical to the formulation of A1 as expected because we're recalling A1. And then we're recalling the other axiom that Sophia exists. So now we have 2 lines, one saying that everyone has a friend and the other saying that Sophia exists. So it's actually something we are given. Sophia is something that we are given. The question is how to then conclude from this that Sophia has a friend. So here we're told that everyone has a friend. So if Sophia exists, then Sophia could be one of those everyone, right? So the deduction rule we will use here is the one we are already familiar with, the .d rule that allows you to, so D here stands for deduce. And by the way, C stands for recall, but I didn't want to use R because R is reserved for something else. So C is for call then, for the 3rd letter of recall. .d is going to take this line and apply it in the case when in the place of X we have Sophia. And so as we know the parameters, the first parameter, it tells us the thing we're applying, which line it comes from. It's line 1. So that's why we have number 1 here. Then we have to tell Sophia the free variable we have here, the X, right? Which could have any value, because remember, this is saying for every X, right? We're telling the computer exactly what I want my X to be concretized to. And the coordinates are given to whatever X should be concretized. The coordinates are 2, 1. That means second line. So you see line 2, position 1. So 1 stands for position 1. There is only one thing, one statement in the second line, so it will automatically just produce this. So basically then we're saying that I want to apply this fact that everyone is a friend in the specific case of Sophia. And so as a result of application, because the assumption part is already something we have guaranteed in the second line, then the computer just returns for us the second half. So since in the first line, we said that whenever I have this, I can also get this, right? But now I have that the thing I have is Sophia. So I can get this, the second part, for x being equal to Sophia. And that's what we see here. However, something interesting happened. The variable y now became y prime. Why do you think is that? Why didn't the computer just keep the variable y? Why did Sophia have to change y to y prime? So I see that this is not a very easy question. Can maybe anyone still try to guess at least? It's not something that we've explained before. Okay, then I'm going to try. Or maybe Ilya wants to try.
I don't know. Maybe because you already used y somewhere.
That's right, yes. So we have y here. And so the thing is that the scope of this y here is just this. But now when we bring this out there in line 3, whatever we put here, the scope of that will be the entire line. But that also means that the scope of this will also be the other lines as well. I mean, that's something we didn't explain before, but I'm telling this to you now. So when a variable has a scope that's the entire line of my proof, then this variable also has, inside the proof, also has a scope of all the other lines, because in some sense, I mean, all the other lines that are at the same level of assumption depth, and in which case, in this case, it's just one level, so it's no problem. In some sense, that's because every time we move to the next line, we should consider all the previous lines as just statements put next to each other. So it's just like one long statement. So by the time we're in line 3, we actually have 3 statements already established, which is this one, and that one. And if you look at the definition of scope, if we think of that as one long statement, the scope of y prime would be the entire thing. But that means that this y here, whose role was to say that something will exist, now becomes fixated to this external y that will appear here. And I don't want that. I still want this to be saying that something exists, not necessarily some other y that I already have. No? And so that's why when this thing is brought out in line 3, the name of the variable had to change. Imagine we had a second statement like this, which says that some other y exists for some different reasons. And this y prime that we have here, which comes from a completely different place, why should that y prime now be the same as all the other y's we had before, right? That would be not correct to believe that all the y's that exist just because they're called y's, they necessarily all need to be the same object, right? So that's the idea here. Okay, that completes the discussion of this proof, because we've now proved what we wanted. And so this last line we get is exactly the statement of the theorem. And the reason for this is because when the proof ends with a line that doesn't have any assumption depth in it, so there was no assumption introduced in this proof, so assumption depth has been 0 all the time. then in that case, the last line of the proof is considered as the statement of the theorem as well. So we see that this has been copied there, and this is all we want, because this exactly says that Sophia has a friend. The friend's name is y prime. So this statement says that we have a y prime such that y prime is friends with Sophia. Are there any questions about this specific theorem and how we use the axioms to prove it? Great.
I think everybody is happy, and user up is 100%, not 100%.
Yes, I'm sorry about that. I'm coughing every now and then. Sometimes I'm trying to mute myself, but it doesn't work all the time.
Okay, no worries, but get better.
Okay, so then we're going to move to the next topic, which is a very interesting topic. And after this topic, we would have covered all of the features of Sophia that one needs to formalize any part of any science that's precise enough that you can mathematically formalize it, including mathematics itself. So there is one last thing we need to learn, one last type of deduction we need to learn, which would enable to capture all of mathematics and hence all of science. And this has to do with the concept of fallacy, in other words, falsity or contradiction, if you like. So I've written up a section on this. This is the new section that's added to the notes, section 9. First, let's introduce notation, and then we're going to start talking about what it means. The notation is this: exclamation mark, open bracket, close bracket, and another bracket there. When it's stated, without the statement, it's just the formula is just this. These brackets here are there to give me a constant, so that the exclamation mark is not a variable. Okay. So this constant is going to be called fallacy. You can synonymously call it falsity, although I don't think the word falsity exists. You can also think of it as absurdity. It will be a tool for saying that something is false. Remember, we already have a tool for saying that something is correct. It's the idea of stating it. So when I want to say that apple is green, if I just put it like this, it's only a formula. I'm just wondering about apple being green. Okay, great. So falsity does exist. It was a post in the chat. Thank you very much for that. So if I want to now not just wonder about apple being green, but just claim apple is green, then I'm going to turn it into a statement. So we already have a tool for making a claim that something is true. What about claiming that something is false? Now this takes us to the question of what does it mean for something to be false? Does such a thing even exist? Can we even claim about anything that's false? Huh? Well, one can say the same thing. I mean, what does it mean that something is true? So it's our emotion we have that something is true, and we have emotion of something being wrong or false, and we want to express these emotions because these emotions are the kind of basic building blocks for logic, right? So the way we're going to do this is the following. In fact, this is not anything that I invented. It's the way it's done in mathematics, and it's the way it's been done in mathematics since mathematics has obtained a formal foundation. So to say that apple is green is false is done in the following way. And to turn it into an actual statement, we need to put another brackets. So let's try to explain why this is the right way. What does it tell us? It tells us, of course, we know what does colon stand for. It's for implication, right? So it tells us that if we believe apple to be green, then, so this is the if part, then we're going to conclude absurdity. Yeah, does it make sense intuitively? So basically, in mathematics, something is false when you can derive contradiction from it. That's one way of thinking about it. But the question still is, what is this? It's an abstract entity we sort of invent to represent anything that's absurd, anything that we want to believe to be, that we believe to be false. Okay. So for instance, this could stand for 1 equals to 2. Or it could stand for the earth is flat, and so on. But surely we can't just pretend that this thing is absurdity. I mean, if anything can be written here, even things like this, then why couldn't we write instead something of this kind? I mean, there must be some feature of this formula that will make it behave like falsity should behave. And that feature is an axiom. The axiom says the following, but before going into what it says, let's answer a question. Yes, please.
Yes, thank you, sir. Actually, I want to ask, since we're talking about fallacies, we also want to touch on paradoxical statements. For example, can Sophia maybe be used to show whether something is a paradox? Say maybe someone says this statement is false.
Yes. So paradox is exactly where we begin with some assumption and we are able to derive absurdity from it. So we're able to derive falsity from it.
Okay.
That's
I'm
the
thinking
paradox.
Like the example of maybe the Bertrand Russell's paradox. Who cuts the barber? So things like that. Like, are we?
Yeah, we did that. We did that Russell story. One of the lectures. We had a specific lecture in which we went in detail to the Russell's paradox story. We slightly modified it. We called it paradox of ideal teacher. But in the lecture, in the recording, I also explained the link with Russell's paradox.
Okay.
I think it was done in the section on constants. So you might want to look at this. So this is basically Russell's paradox. But we didn't, it turns out that for Russell's paradox, we can formalize this idea of Russell's paradox without necessarily using falsity. But we could, so instead of falsity explicitly, we use this statement, the world is flat, as an example of an absurd statement. But for Russell's paradox purpose, the world is flat didn't have to be false. The proof would still be correct proof deriving the paradox. I mean, in this case, deriving that the world is actually flat if such barber exists. But for many other mathematical theorems, we will need to make use of the fact that the world cannot be flat. And that's what we're doing in this section. So to link up what we're doing now with what we did before, one would have to revisit this exercise, replace the world is flat, this statement with falsity, stated version of falsity, and then you'll get Russell's paradox proof, basically the proof that existence of the barber leads to paradox. And if you want a barber and not a teacher, then instead of teaches, you say shaves. So that's another replacement you would want to make. Okay.
Thanks.
So let's look at the axioms involving falsity. And here is one. There are actually two different ways of thinking about this axiom. And I'm going to, two different illustrations rather of this axiom. I'm going to copy paste both of them. Okay, so this is the other one. Sorry, I wanted to discuss, for us to discuss, not this. There are two axioms related to falsity, and I got the wrong one from the notes. The one I want is F. So let's call this C. Let's not worry about these two for now. And let's put here, once again, the world is flat. And let's see what happens. So we have an axiom which says what? That if we assume falsity, right? Then remember is colon is implication, right? If we assume falsity, then from this we can derive that the world is flat. In other words, we're saying that from absurdity, basically anything can be concluded. I could put here, instead of the world is flat, I could put here anything else I want. I apologize, this WhatsApp, I should turn it off, sorry. There we go. I could put anything else I like. Ice cream is warm. And we'll have that axiom as well, saying that from absurdity, ice cream is warm can be derived. So the moral of this story is that absurdity is a mathematical statement from which every other thing can be derived. And that is a valid rule that we're going to believe in to build the rest of mathematics up. This rule works. Why does it work? This rule that absurdity allows to derive everything is one of the inseparable foundations of a lot of mathematics that has been tested in physics, for example, to work in real life. So it's just part of our universe in some sense that this rule works. But who knows, maybe after 200 years, we will have completely new perception of the physical universe. We will discover that there's actually one exception where this rule doesn't work. And then if there is one exception, it means it doesn't work at all. We don't know that yet, but so far it works. Even in trying to understand quantum physics, the rule still works. Okay, and not just works, we need this rule for deriving a lot of mathematical principles, which are important for applications. But it is yet, nevertheless, it's a bit counterintuitive idea. And you might have already encountered this idea in some maths courses you might have done, where the teacher would have told you that, or maybe you yourself are a mathematician, that you would know that this rule in mathematics that false implies anything. There are truth tables one draws up and so on and so on. But despite of all of this, you might still have some discomfort with the rule, and we can have just a little bit of time discussing, if you do have the discomfort with this idea of absurdity logically implying anything. So if you want to ask a question about this, please go ahead. Okay. The second axiom that involves absurdity, in other words, falsity, the second type of axiom is the one I had before that I erased. Let me bring it back. Actually, I only did this line. It's this one. Now let's try to understand what this says. In order to do that, we will have to go back to ontology. So I'm going to copy this, paste it here. Once you're used to Sophia language enough, then you don't need to draw this ontology all the time. Then your eye recognizes immediately what the statement says. Maybe not always immediately if it's very long, but at least it works well enough for examples we're considering. So this bracket seems to match with that, right? So we separate this one out first. Now we see that this bracket here matches with that. And there is no other bracket there. So certainly then, surely then, that whole thing must be together. Then again, this bracket matches with that. So we separate this one out. And once again, for similar reasons, no, not so easy to see. Yeah, so this one is together and the other one is together for similar reasons as before. And let's not go further. Let's just stop there, because that will be enough for us to understand what the meaning of the original statement is. So let's just label our ontology diagram. So the first one was a statement. The second line was a formula. Then we had two statements there. So these were statements. And then we had, so there is more here, but I'm not breaking it down further. On this side, we have a single formula. And then we have statements. There we go. Yes, there's a question there regarding absurdity. Does it mean that with flawed logic, anything is true? That's true. That's what it means, yes. So if you discover a universal principle from which everything else can be derived, mathematicians will simply tell you that what you're saying is false, because that's the definition of falsity. A principle from which everything can be derived. Okay. It's philosophically, it's a significant thing, what I just said, and counterintuitive as well. Okay, so let's now try to understand what we're talking about here. So we're saying here, if X is nice, then absurdity, right? this is the way we say when something is false, that we already said before. So this whole thing basically says X is not nice. If it was nice, we could derive from it absurdity, and that's exactly the meaning of something not being true. So in general, when I want to say that alpha is not true, in mathematics, the way we say this is that from alpha, we can derive falsity. Maybe we can put implication in standard mathematical language. In the Sophia language, this is colon like we use here. So something being not true means that we can derive falsity from it. Okay, I should be careful with the use of colons here. So that's what this says. It says X is not nice. But then, what does this thing say? Would someone like to give it a try to answer this question? So I explained why this thing means X is not nice. Next question is, what does this mean?
I think it's a double negative.
That's right.
Yeah, okay.
That's right. It says that this thing says it is not true that X is not nice, right? It is not true that X is not, that's what it says. Every time I am deriving absurdity, I'm negating my statement, right? So here I'm doing it twice, and therefore I'm negating twice. Okay, so that's what this says in the formula form, and then stating it gives us this, and that one says X is nice, and then here we're saying if it is not true that X is not nice, then X must be nice. So we're basically saying that double negation cancels out. If I negate something twice, it means that I'm claiming it's true. And this is not something to be taken for granted. It's one of the axioms of logic. There is a lot of mathematics that can be done without this axiom. There are many names that refer to this principle. One of them is law of excluded middle, for example. This axiom helps us a lot with proofs by contradiction. Very often I want to prove something is correct. So I'm going to assume it's wrong and derive a contradiction from it. But deriving contradiction from assuming it's wrong, it's just double negating. But then from that double negation, I want to recover back and say, okay, because I proved double negation of my statement, now I want my statement to be true. And I can only do that by applying this axiom. And we want to have this axiom not just for X being nice or not being nice, but for any other statement, right? Any other Sophia statement. So that's why these axioms here, they have parameters. You see, we enter the whole statement basically for which I want to employ that kind of axiom. So for instance, the one we were discussing right now is this. And if I put here, instead of X is nice, I put something else, maybe South Africa is beautiful, right? Then it will generate for me, let's actually try what it will do. South Africa is beautiful. I'll run it. It will generate an axiom that has same structure as the one before. Instead of X is nice, it says South Africa is beautiful. So South Africa is beautiful, implying absurdity, and that thing implying absurdity, in other words, double negation of South Africa is beautiful, should give me as a consequence that South Africa is beautiful. So the double negation rule is now used for South Africa is beautiful. And so I would want to use this rule for any other statements as well. That's why I need to enter it as a parameter. So this is an example where an axiom requires parameters of its own. And so a tool in Sophia that creates axioms out of parameters like this one is called an axiom builder. Axiom builder is implemented in the Sophia module here, right at the bottom, this thing here. It's called bool because bool stands for Boolean logic. These two axioms come from Boolean logic, if you know what Boolean logic is. I'm showing this to you because in case you want to build your own axiom builders for various mathematical theories, some mathematical theories require infinitely many axioms, in other words, parameterized axioms, and so you can achieve that by incorporating axiom builders. So you see, we never introduce this axiom using that proposition object anymore. That is done inside the, when we call this function, let's say the n function, .n function. If you look at the command here, .n function, it creates a Sophia proposition I, but then it, the way it postulates it, the way the text of the axiom is stated, depends on the parameter that has been entered. The parameters are the start and context. Also, the context parameter is something we're not going to explain today, but you can read up the explanation of it in the lecture notes. And then that axiom is returned with a function. And so what we are seeing here is still a Sophia axiom, but it has been instantiated inside this function, which we call an axiom builder. Okay. Where do we go from here? We have one very, very interesting, complicated a bit, maybe too much complicated example of using the axiom we just proposed, specifically the double negation axiom, to establish some fact which intuitively could seem very obvious, but if something is intuitively obvious, it doesn't mean that it's obvious to mathematically justify it. For example, it took a while for Isaac Newton to justify why did apple fall from the tree, right? And we will now see how we can do that using the tools we've developed so far. Not for the apple, but for this simple theorem from geometry. Okay, any questions so far? I'm going to copy all of this text. You see, it's a long proof. And I forgot to, it didn't run because I forgot to import Sophia. Still didn't run. Let me see why. Maybe I didn't copy everything. Yeah, I didn't copy the entire thing. Sorry. There we go. This proof looks very complicated and very dense, right? So we're going to start with a simpler version of it. So there are two simplification of these steps in two steps, so to say. So the first one in the notes that you'll see basically takes the same proof as here with its vertical bracket structure, but rewrites it, eliminating the bracket notation of Sophia and turning each step of the proof into a more intuitive statement using just English language, okay? So that's the first step of simplification. And in the second step of simplification, we get rid of kind of those steps which we can add routinely once we go back to the formal Sophia proof. And it is here where we will be able to get the insight of what's going on in the proof, the intuitive insight. So someone who is trying to discover this proof for the first time, they wouldn't be able to do this. This is too complicated to discover for the first time. They would make a sketch for something like this. Even something actually even shorter, as I will show you. And then once you've got this, like a question was asked before, once you've got this, then you slowly try to make it more precise by adding some missing lines. You get something like that. And then you're finally able to make it fully precise by implementing in Sophia. Okay, so let's begin with this. But first, let me state what we're trying to prove. If we look at the source code here, this is something we already talked about. This is the Boolean axiom builder. We will use it because we're going to use one of the axioms we just discussed. Then there are two things that's happening here. One is you see .p command. It means that axiom is being formulated. So I to C is an axiom, and then it will be used to prove a theorem. And so I'm going to explain now what the axiom says, what the theorem will be, and even before we start proving anything, so we can visualize the whole situation, so we get an intuition of what's going on. So this material comes from a field of mathematics called incidence geometry. It's a subfield of geometry which studies straight lines, planes, and other possibly higher dimensional objects by looking solely at the interaction of when is one space contained in the other, okay? And in that realm, a very natural axiom to have is that if we have a plane, so remember intuitively a plane is a flat surface, right? If you know what is Euclidean geometry, then the plane there is any subspace as well as any subspace shifted by a certain vector. So the axiom says, I'm reading this one, plane has three non-collinear points. The axiom says that whatever plane you've got, you can always find on that plane 3 points that do not lie on the same straight line. So as soon as you have 2 different points, we know we can have a line between them, right? And then we just have to take a point that's outside that line to achieve this goal. So it seems to be a very natural requirement to have that on a plane, we can find 3 points not lying on the same straight line. In fact, in incidence geometry, this even becomes definition of dimension of space. Plane is 2-dimensional because there are 3 such points. In a 3D space, you'll have 4 points not lying on the same plane. And so the dimension is 1 less than the number of points. So this is our axiom that a plane has 3 points on it which do not lie on the same straight line. The theorem we're going to prove says that there is a point outside any line or a plane, and we're just going to, well, actually both parts are done here. Yeah, so the theorem says that if I begin with some line or plane, let's say I begin with a line, okay? It will always be possible to find a point that is outside that line. Okay. And it also says no, sorry, I'm sorry. My COVID brain is making me misread what I wrote myself. The theorem is the following. If I have a plane, remember a plane is not finite, right? It continues infinitely, unless we are dealing with finite geometry, which is possible, but we're not going to look into that now. So if I have a plane and I have a line on it, outside that line, we will, inside the same plane, but outside the line, we will always be able to find a point not lying on the line. Okay, so starting with a plane and a line on the plane, we can find a point on the plane that's not on the line. That's what the theorem says. The axiom says, starting with any plane, we can always find 3 points not on the same line. Now, do you see, intuitively at least, would you be able to explain, if we believe this axiom to be true, how we can derive then from it the theorem? Do you see that? So let's write the statements down. So any plane has 3 non-collinear. Non-collinear means that they lie on the same line. Non-collinear means that they don't lie on the same line. Non-collinear points. And the theorem says, for any line on a plane, there is a point on the plane that falls outside the line. So do you think you can explain why this claim here can give us as a logical consequence, without using any other insight of geometry, just using this fact and pure logic, how can that give us this? Why does this imply that?
Okay, Prof. I think that since we know that those 3 points do exist, maybe we can deduce that a line can only pass through 2 points. So there's always going to be a dead point outside.
Fantastic. Perfect. Let's first make sure everybody else understood this before we move on. So is there anyone who didn't understand the explanation we just heard? So let me maybe re-explain it by drawing at the same time so it's easier to follow. So you said that we know that there are 3 points on this plane. Let's draw them in. Now, out of these 3 points, at most 2 might accidentally end up lying on that line. The third one cannot end up lying on this line because by the axiom, the 3 points cannot lie on the same line. They're non-collinear points. So it then must lie outside the line. Is this a good explanation of what you meant?
Yes, exactly.
Mm-hmm. So does everyone understand this? So please say yes or no in the chat. Okay, well, there is at least one yes. But if you don't, please ask. Now, as obvious as this may seem, there is from the point of view of logic, there is a lot going on. And all of these things that's going on, I mean, there's really a lot going on because this is how the proof looks like, okay? And the fact that you were able to say what you said, right, is because subconsciously your brain did all of this. And now we want to go into that subconscious and uncover the primitive steps. Just to show you one possible thing that we kind of quickly overlooked is that it doesn't matter the order in which we consider these 3 points. Because the way I was drawing it, the first point was this, the second, the third, but it could have also been that the first point is the one that lies outside, or the second one is the one that lies outside, right? We didn't consider these cases because it felt obvious that the other cases are going to be similar. But in Sophia, there's nothing like that. We'll have to explicitly consider cases. In fact, we will have a way around cases by using proof by contradiction, as we will see. Okay. I think at this point, we are ready to look at the proof that's formalized, not quite the fully formal one yet, this version. So let me zoom in here and let's try to follow this line by line. And I'm going to make drawings as we follow the proof. In fact, I'm going to make a drawing right here on top of the page. In the first line, we're saying, consider a line L in a plane P. Well, that makes sense because we want to prove something about any line on a plane, right? So let's say this is a plane P, and we have a line L. So this is our line L, lying on the plane P. In the second line, we're saying by the axiom that every plane contains three non-collinear points, there are three distinct points A prime, B prime, and C prime in P, which never lie on the same line. I'm going to draw them separately because at this stage, I don't know what the relationship of A prime, B prime, and C prime is with L necessarily. So I'm going to draw the same P, and on the same P, mark 3 points, A prime, B prime, and C prime. So that's by the axiom, right? So that's the second line of the proof. Then something interesting is happening in the third line. We're going to assume that every point in the plane lies on the line L. Why do we want to assume that? Because we want to derive a contradiction from it, and we want to eventually prove that it's not true. You see, if we look a bit into the future, we're afterwards saying that this proves that not every point of P lies in L, which is good because it means there will be a point that does not lie on L, right? Oops. Oh, sorry, I erased everything. Okay, it wasn't a good idea to draw here. There we are. So we started with a plane P, a line passing through it L, and then we in the second line of the proof. So this was the first line of the proof. Let me still label the lines of the proof. Oh, it is actually labeled already. Here we have labels, so we don't have to label them separately. In the first line of the proof, we have this setup. The second line of proof applies the axiom to produce 3 points, A prime, B prime, and C prime. And then we are assuming that all points of the plane P lie on L. That happens in line 4. These labels of lines actually correspond to the labels in the Python code. So that's why the second line here, for example, captures 2 lines of the Python code. That's why they're numbered like this in a funny way. So assuming that every point lies in L, from that we will be able to conclude that in particular, these 3 points lie on L as well, right? If every point of plane P lies on L, then those 3 will also lie on L, right? Oh, but if they lie on L, that's a contradiction because remember we said by axiom, they can't lie on the same line, yeah? So that's how we arrived to this contradiction, this line which is labeled L9. So we now know that not every point of P lies in L. But is that what we want to prove? We want to prove that there is a point in P that does not lie on L. But what we proved so far is that it's not true that every point of P lies in L. So are these two things the same? And logically, they are the same. but it still takes a proof to establish they're the same, and the rest of the proof does that. Okay, now we can go back to the fully formal proof to this one, but we're going to build it up step by step. So I'm going to gray out the lines we're not interested at this point. Sorry, I'm fixing up my microphone here. There we go. We begin just with the assumption. We will probably not have time to go through all of this proof, but then the rest you can do in your own time. But we'll have time to cover a substantial part of it. Great. So our first line of the proof, it's an assumption. It gives us L. This is not number one. This is L. A P, a statement that L is a line. So we're given a line L. Statement that P is a plane. So we're given a plane P. And statement that L lies in P, and that we write it in short as in. Good. So that's exactly the first setup we wanted to start with, right? Let's look at the next line of the proof. Now I'm going to uncomment this one. Before reading what the line says, I want to read the explanation of what kind of line is it. And it tells me this is recalling I2. What is I2? It's the axiom we talked about earlier. Okay, so then I don't need to read this fully because I already have the axiom in my mind. I know what it says. There's no need to go through this one more time. Even though we didn't go through the axiom, actually, we could have done that by drawing ontology and so on. But let's keep that for now. Next line. Let's see what next line does. Next line is application of L2.1. L2 refers to the second line. So the second line is when we recall the axiom. So it will now be applying the axiom, right? And now let's see what the result of the application of the axiom is. We have here A prime, B prime, C prime. These are going to be the 3 points. We are told that they're different from each other. We can recognize it like this because it says if they're equal, then we can conclude absurdity from it. So that's a way to say that they're not equal. So this tells me that A prime and B prime are not equal. In fact, this proof does not really need for us to have that part of the axiom. So it's a bit extra information, which in the end we will not need. Let us know that let's work with that. Then the second, the statement after tells me A prime, C prime are different from each other. Then the nice thing about Spider also is that it gives you the scope of the brackets so you can recognize the statements here. The one after tells me that B prime and C prime are different from each other. So these 3 points are all different from each other. Then we have statement that A prime is a point. Okay. A prime is a point and C prime is a point. A prime lies in P, B prime lies in P, and C prime lies in P. Great. Remember what the axiom says? The axiom says that every plane will have 3 points which do not lie on the same line. Now I want to, I've already identified 3 points. Now I want to say that it's impossible for those 3 points to lie on the same line. And let's see how we do this. It's done basically here. This statement decomposes into a formula with an implication here. And so it will say that something is not possible because you see after the colon, we have absurdity, falsity, right here. So what is impossible? It's impossible to have L prime, that's a line on which A prime lies, as well as B prime lies, as well as C prime lies. So basically it says it's impossible to have a line on which all 3 points lie, right? That's exactly what I want to say. So now that we've applied the axiom to our plane P that we are given in the beginning, we now have on this plane, we have now 3 points, A prime, B prime, C prime, and we can proceed with the proof. If there are any questions so far, please feel free to ask them. Okay, great. The next line. The next line is this assumption that we talked earlier, that we're now assuming that, you see, again, there is this colon here. So variable appearing on the left side of the colon for the first time. That means that we want to say for every, right? Because if we're given a D, that's a point, and that lies on our plane P, then it must follow that D must lie on L. So this says that every point that lies on P must definitely lie on L. This is what we will prove to be impossible, as we did in the shorter version of the proof. The line after is application of what? Of line 4, exactly this one. So we're going to apply this in the case of our specific point A prime. In order for Sophia to apply this, she needs to be able to find all of this for a specific value of D that we specify. All of this has to be present. But for A prime, all of that is present. Firstly, A prime on its own exists because it's stated here. A prime being a point is stated right here. And A prime being in P is stated right here. So once all of this is confirmed, then Sophia can say, aha, therefore, indeed, we can then believe that this is also true, namely that A prime is in L. In exactly the same way, we can get B prime and C prime also to be in L. See, we produced the two more lines here with B prime and C prime. And now that we have A prime, B prime, and C prime, all of them being in L, that is the contradiction, right? Because according to the axiom, that should not be possible. So then application of that part of the axiom that says it's not possible is used here. An application of that gives us, as a conclusion, absurdity. So starting with this, we were able to conclude absurdity. And then we do synopsis to summarize this. So now we know that having it true that every point lying on the plane also must lie on that line, that thing is false. But that is different to saying that there exists a point outside the line, right? Remember, if we're saying that there exists a point outside the line, we should have the variable on the right side of implication. This is for every, huh? So to switch that around from one side to the other, this is exactly where we will have to use the Boolean axioms. So we will, the way it's done is that we're going to assume that it's not possible. So in this assumption, we're proposing that the existence of D, that's a point that lies on P and that does not lie on L, right? Existence of such D is impossible. And using some steps, which we're not going to go through now, we're going to go through that tomorrow. We will conclude that, so these steps will be done tomorrow. We will conclude that that thing is itself absurdity. In fact, it takes a few more lines to do that. And so eventually we will be able to get this, which says that every point that lies on P also lies in L. But remember, we already proved this is not possible. So that was going to give us contradiction. And this contradiction okay, so this line is recalling the Boolean axiom. I realize that it's no longer possible to follow what I'm talking. Maybe I shouldn't have done this. but eventually we're going to get to a point where, okay, yeah, it was not a good idea for me to skip through this. So we arrived to a place where we made the assumption that what we want to prove, the opposite of that is true, and then from there we will come to a contradiction and hence conclude that what we wanted to prove is actually true. That's something we're going to continue with tomorrow. Okay, I think that's it from my side. If you have any questions, we can, I think we can for a few minutes discuss them, otherwise. I think there are no questions, Ilya, so you can take over.
Thank you. Yeah, I think that probably, yes, you are right. And the last bit was a little bit rushed up. And maybe if you can go into the more details during your tomorrow's lecture, that would be much better. And the students could understand it nicer. Yes. And what I need to do, I need to thank you. Yes. And I thank you very much for the very interesting lecture, and it would be really nice to see, like, you know, kind of it's getting more and more to the kind of proving some statements which kind of many, at least for me, is like more sounds like a statements which requires proof, kind of more complicated, and that's very interesting. Thank you very much. And I just would like to remind to all the participants that Zurab will continue tomorrow morning, so his lecture will be at 9 o'clock tomorrow. Thank you very much. Bye-bye.